In the deepest space between galaxies, something incredible is happening. Every cubic inch of emptiness contains enough hidden energy to power our civilization for billions of years. Virtual particles appear from nothingness, borrow impossible amounts of energy, then vanish before the universe notices. We'll journey through laboratory experiments that create light from pure vacuum, discover cosmic voids that stretch across 300 million light-years, yet teem with invisible forces, and explore how the very emptiness around you could suddenly rewrite the laws of physics faster than light. If you enjoy mind-bending science, hit that like button and subscribe for more cosmic mysteries. Prepare yourselves. We begin. Your coffee cup sits on your desk, apparently empty, but it contains quadrillions of air molecules racing around at 1,500 miles per hour. Most people think empty means nothing exists there. Walk into what seems like an empty room, and you're actually swimming through an ocean of nitrogen and oxygen molecules. Each breath you take contains roughly 25 quintillion molecules. These invisible particles crash into your skin about 10 trillion times per second, creating what we feel as air pressure. Think of air molecules like microscopic ping-pong balls bouncing everywhere at incredible speeds. In your seemingly empty coffee cup, these molecular ping-pong balls zoom around faster than a speeding bullet. They slam into the cup's walls millions of times per second, each collision so tiny you can't feel it. But together, they create enough force to support the weight of the entire atmosphere above us. Room temperature means these molecules move at about 500 meters per second. That's faster than the speed of sound. When you wave your hand through empty air, you're actually bulldozing through countless molecular collisions. Your hand hits roughly 1 followed by 23 zeros worth of air molecules every single second. Temperature is just the average speed of molecular motion. Hot coffee heats up nearby air molecules, making them bounce around even faster. Cold air contains the same molecules, just moving more slowly. Even at the coldest temperatures humans have ever created, molecules never completely stop moving. But air molecules are just the beginning of what fills seemingly empty space. Like these fields carry energy and can push on charged particles, even when no matter is present. Scientists have discovered that even the most perfect vacuum still contains something extraordinary. Remove every last air molecule, every photon of light, every electromagnetic wave, and something remains behind. The quantum fields that create all matter and energy never completely disappear. They keep fluctuating and vibrating, even in the deepest emptiness. Modern physics reveals that perfect nothingness cannot exist. The universe abhors a true vacuum more than nature supposedly abhors a regular vacuum. Quantum mechanics demands that energy levels always fluctuate. These fluctuations happen so quickly that they seem to violate conservation of energy, borrowing power from nowhere and paying it back before reality notices the missing energy. Your coffee cup demonstrates how wrong our intuitions about emptiness really are. What looks empty actually buzzes with invisible activity. Molecules race around faster than fighter jets. Electromagnetic fields weave through space. Light and radio waves stream through continuously. Even if you could remove all of this, quantum fields would keep the space from being truly empty. The deepest vacuum chambers humans have ever created still contain thousands of particles per cubic inch. Perfect emptiness remains beyond our technology. Yet, even if we could create a perfect vacuum, something would still be there. But compared to what exists between atoms inside solid matter, your coffee cup looks crowded with activity. The gap between the nucleus and electrons in a single carbon atom could fit 10,000 virus particles lined up side by side. Atoms are mostly empty space. If you enlarged a hydrogen atom to the size of a football stadium, the nucleus would be a marble sitting at the 50-yard line. The single electron would be a tiny speck orbiting somewhere in the stadium's upper seats. Everything else? Apparently empty. This emptiness makes up nearly all of the matter around you. Your coffee cup, your desk, even your own body consists almost entirely of empty space between atomic particles. The actual matter that makes up atoms takes up less than 1/1,000,000th of their total volume. You are basically a cloud of emptiness held together by electromagnetic forces. Scientists once thought this atomic emptiness was truly empty. Early models pictured electrons orbiting the nucleus like planets around the sun, with nothing but vacuum in between. These planetary models seemed to explain how atoms worked, but they missed something crucial about the nature of space itself. Quantum mechanics revealed that atomic emptiness seethes with activity. Even at absolute zero temperature, when all molecular motion stops, the electromagnetic field between atomic particles keeps vibrating. These vibrations represent the lowest possible energy state, called zero-point energy. Every point in space, even the empty regions inside atoms, contains this irreducible quantum energy. The amount of zero-point energy hiding inside atomic emptiness defies comprehension. Physicists calculate that every cubic centimeter of empty space contains enough quantum energy to boil all the water in Earth's oceans. A coffee cup's worth of quantum vacuum energy could power human civilization for millions of years. The space inside your body contains more energy than all the stars in the visible universe combined. This energy comes from quantum field fluctuations. Unlike classical physics, where empty space has zero energy, quantum physics requires uncertainty in energy levels. The more precisely you try to measure the energy in a region of space, the more uncertain that measurement becomes. This uncertainty translates into constant energy fluctuations, even in perfect emptiness. Think of quantum fields like the surface of a stormy ocean that never becomes perfectly calm. Even when no waves are visible, tiny ripples keep the water moving. Quantum fields behave similarly, with fluctuations happening at every point in space and time. These fluctuations create virtual particles that pop into existence and immediately disappear. Virtual particles aren't science fiction. They represent real disturbances in quantum fields that scientists can measure and predict. Virtual photons carry electromagnetic forces between charged particles. Virtual electrons and positrons briefly appear in strong electric fields. These phantom particles influence real physical processes, from the behavior of atoms to the properties of empty space itself. The electromagnetic field that holds atoms together depends entirely on virtual photon exchanges. When two electrons repel each other, virtual photons carry the repulsive force between them. These messenger particles exist for impossibly brief moments, violating energy conservation laws for tiny fractions of a second before disappearing. Every chemical bond in your body relies on virtual particle exchanges happening trillions of times per second. The forces that keep your atoms from flying apart depend on this quantum vacuum activity. Life itself exists because of phenomena happening in supposedly empty space. Yet, even this incredible atomic emptiness pales in comparison to what scientists have discovered lurking between the subatomic particles themselves. A virtual electron-positron pair can borrow enough energy to equal the mass of a planet, exist for less than 1/septillionth of a second, then vanish without a trace. The quantum vacuum operates like the universe's most exotic bank. Virtual particles constantly withdraw massive amounts of energy from nothingness, but they must pay it back so quickly that reality never notices the missing funds. This quantum lending system powers the fundamental forces that hold matter together. Heisenberg's uncertainty principle allows these impossible transactions. The principle states that energy and time cannot both be measured precisely. The more accurately you try to measure energy in a specific moment, the less accurately you can determine when that measurement occurred. This uncertainty creates loopholes in conservation laws. Virtual particles exploit these loopholes by borrowing energy for incredibly brief periods. The more energy they borrow, the shorter time they can exist. A virtual particle with the energy equivalent of a hydrogen atom might exist for about 10 to the negative 21 seconds. More massive virtual particles must disappear even faster. These energy loans happen everywhere, all the time. In the space between your fingers right now, virtual photons, virtual electrons, virtual quarks, and dozens of other virtual particles continuously pop into existence and disappear. Every cubic centimeter of empty space experiences roughly 10 to the 45 virtual particle events per second. Think of virtual particles like lightning that strikes in reverse. Instead of building up charge over time and releasing it in one dramatic flash, virtual particles release enormous energy instantly, then spend almost no time existing before vanishing. They're like cosmic fireworks that explode before they're lit. Virtual particle pairs usually appear together and immediately annihilate each other. An electron and positron might briefly materialize, circle each other once, then crash together and disappear. The total energy borrowed equals 0 because the electron's negative energy cancels the positron's positive energy. These paired appearances and disappearances maintain overall energy conservation, but sometimes virtual particles don't get to annihilate their partners. Near black holes, one member of a virtual pair might fall past the event horizon while its partner escapes into space. The escaped particle becomes real, stealing energy from the black hole to pay its quantum debt. This process, called Hawking radiation, allows black holes to slowly evaporate by losing energy to virtual particles. Strong electromagnetic fields can also separate virtual pairs before they annihilate. Physicists have predicted that powerful enough electric fields could rip virtual electrons away from virtual positrons, creating real particles from pure vacuum. These fields would need to be stronger than those around atomic nuclei, but they might exist near neutron stars or during cosmic collisions. Laboratory experiments have detected virtual particles indirectly through their effects on real matter. Virtual photons slightly shift the energy levels of hydrogen atoms, creating measurable differences in the light they emit. This Lamb shift provided early evidence that quantum vacuum fluctuations really occur. Virtual particles also influence the magnetic properties of electrons. Clouds of virtual particles constantly surround real electrons, slightly changing their magnetic strength. Precision measurements match theoretical predictions perfectly, confirming that virtual particles aren't just mathematical tricks, but represent genuine physical phenomena. The strangest aspect of virtual particles is their ability to carry information faster than light. Virtual photons can briefly travel at speeds that would be impossible for real photons. This doesn't violate relativity, because virtual particles can't carry messages or energy over long distances. But these phantom particles have revealed something even more surprising about the nature of space itself. Two metal plates, suspended in perfect vacuum with a gap thinner than a human hair, will spontaneously slam together with measurable force. Dutch physicist Hendrik Casimir predicted this bizarre phenomenon in 1948 by carefully analyzing virtual particles. He realized that empty space between closely spaced metal plates contains fewer virtual photons than the space surrounding the plates. This imbalance creates a net force pushing the plates together. Think of virtual photons like invisible ocean waves with different wavelengths. In open space, waves of all sizes can exist freely, but between closely spaced metal plates, only waves shorter than the gap between plates can fit. Longer waves get excluded, like trying to fit a full-size surfboard through a narrow doorway. The excluded waves create an imbalance. Outside the plates, all wavelengths of virtual photons push outward in every direction. Inside the gap, only short wavelengths can push the plates apart. The result is a net inward force, squeezing the plates together. Space itself becomes a spring that compresses the plates. This force is incredibly weak, but measurable. Two perfectly parallel metal plates separated by 1 micrometer experience a Casimir force equivalent to the weight of a red blood cell pressing on an area the size of a football field. Despite being tiny, this force has been precisely measured in laboratories around the world. The Casimir effect proves that empty space has structure and energy. Virtual particles aren't just mathematical abstractions, but represent real disturbances in quantum fields that can push on physical objects. Empty space develops pressure, tension, and mechanical properties, just like ordinary matter. Scientists have measured the Casimir force using incredibly sensitive instruments. Microscopic metal spheres, suspended by thin fibers, detect forces as small as 10 to the negative 18 newtons. That's like measuring the gravitational pull of a grain of sand from 20 miles away. These measurements match theoretical predictions with remarkable precision. Different shapes and materials change the Casimir force. Curved surfaces experience different forces than flat plates. Some geometries create repulsive Casimir forces that push objects apart instead of pulling them together. Scientists have even proposed using the Casimir effect to create frictionless mechanical systems for nanotechnology. The Casimir effect happens because quantum field theory requires every point in space to have irreducible energy fluctuations. These fluctuations can't be eliminated, even at absolute zero temperature. They represent the minimum possible energy state of electromagnetic fields in empty space. Boundary conditions imposed by metal plates modify these fluctuations. The plates act like walls that reflect virtual photons, creating standing wave patterns between them. Only certain wavelengths can form standing waves in the gap, while all wavelengths exist in open space. This wavelength restriction changes the vacuum energy density between the plates. The energy difference creates mechanical stress in the vacuum itself. Empty space develops internal pressure that pushes the plates together. This pressure demonstrates that the quantum vacuum isn't passive emptiness, but an active medium with physical properties. Modern technology exploits the Casimir effect in micro-electromechanical systems. Tiny mechanical devices must account for Casimir forces that can overwhelm other forces at microscopic scales. Engineers design structures to either minimize unwanted Casimir forces or harness them for specific purposes. The Casimir effect also influences fundamental physics research. It provides experimental evidence for quantum field theory's predictions about virtual particles and vacuum energy. This evidence supports our understanding of how electromagnetic fields behave in empty space. But the Casimir effect represents just one way that quantum vacuum fluctuations reveal themselves in our everyday world. Even if you could freeze the universe to absolute zero temperature, electromagnetic fields would keep oscillating with 1/2 quantum of energy per oscillation mode. Absolute zero represents the coldest possible temperature where all molecular motion stops completely. At -273.15 degrees Celsius, gas molecules freeze in place, chemical reactions cease, and thermal vibrations disappear. Yet quantum fields refuse to become perfectly still. This perpetual motion comes from the fundamental uncertainty principle of quantum mechanics. Position and momentum cannot both be known precisely for any particle or field. If a quantum field had exactly zero energy and remained perfectly motionless, both its value and rate of change would be precisely determined. Quantum mechanics forbids this level of certainty. Think of quantum fields like violin strings that can never be perfectly tuned to silence. Even when no one plays them, the strings vibrate slightly due to microscopic disturbances. Quantum fields behave similarly, maintaining minimum vibrations called zero-point oscillations that never completely disappear. Every type of quantum field contributes to these perpetual vibrations. The electromagnetic field oscillates at every point in space and time. The electron field fluctuates continuously. Quark fields, neutrino fields, and dozens of other quantum fields all maintain their own zero-point motions. These vibrations happen simultaneously and independently at every location. The energy of zero-point oscillations is enormous. Each oscillation mode of each quantum field contributes 1/2 unit of quantum energy. Since quantum fields have infinite numbers of oscillation modes, the total zero-point energy becomes infinite. This infinity creates one of physics' most challenging problems. Physicists calculate that electromagnetic zero-point energy alone contains 10 to the 113th joules per cubic meter. That's more energy in a coffee cup than the entire observable universe contains in the form of matter and radiation. This absurdly large number represents physics' worst theoretical prediction compared to observation. Real measurements show that vacuum energy has almost no effect on cosmic expansion. The observed vacuum energy density is about 10 to the -9 joules per cubic meter, making the theoretical prediction wrong by 120 orders of magnitude. No other scientific theory has ever been this spectacularly incorrect. This enormous discrepancy suggests that our understanding of quantum field theory, or general relativity, contains fundamental errors. Perhaps virtual particles don't contribute to gravity as expected. Maybe space and time have different properties than current theories assume. The vacuum energy problem represents one of physics' deepest mysteries. Despite theoretical difficulties, zero-point vibrations produce measurable effects. The Lamb shift in hydrogen atoms results from electromagnetic zero-point fluctuations, slightly changing electron energy levels. The anomalous magnetic moment of electrons comes from virtual particle loops created by field fluctuations. These effects match experimental measurements with incredible precision. Zero-point vibrations also affect macroscopic objects. They contribute to the van der Waals forces that hold molecules together in liquids and solids. Without quantum vacuum fluctuations, many materials would have different properties or wouldn't exist at all. Some researchers have proposed extracting energy from zero-point fluctuations. These zero-point energy devices claim to harvest power from quantum vacuum vibrations. However, the laws of thermodynamics forbid extracting net energy from systems in their lowest energy state. Zero-point energy cannot be removed without adding energy from another source. The perpetual nature of quantum field vibrations reveals something profound about the structure of reality. Empty space isn't a passive backdrop where events occur, but an active participant in physical processes. The vacuum has properties, structure, and dynamics that influence everything from atomic behavior to cosmic evolution. But these constant vibrations enable even stranger phenomena when scientists manipulate them in controlled ways. Finnish physicists used an array of 250 superconducting circuits to generate real photons from apparently empty space by rapidly changing how fast light could travel through their device. This experiment demonstrated the dynamic Casimir effect, where moving mirrors can convert virtual photons into real light particles. The researchers couldn't physically move mirrors at nearly light speed, so they created an electronic equivalent that changed the optical properties of their system faster than virtual photons could respond. Think of this like shaking a fishnet underwater. If you move the net slowly, water flows around it smoothly, but shake it rapidly, and you create turbulence that generates real waves. The Finnish experiment shook the quantum vacuum fast enough to create real photons from virtual ones. The device used superconducting quantum interference detectors, or SQUIDs, that respond to magnetic fields with extraordinary sensitivity. By rapidly changing magnetic fields, the researchers could modify how electromagnetic waves traveled through their apparatus. These changes happened billions of times per second, faster than virtual photons could adjust. Virtual photons in the device suddenly found themselves in an environment where the speed of light kept changing. Some virtual photons gained enough energy from these changes to become real photons that escaped the device. The quantum vacuum literally glowed with newly created light. The generated photons had exactly the properties that quantum field theory predicted. They appeared in entangled pairs, meaning that measuring one photon instantly determined the properties of its partner, regardless of distance. This quantum entanglement provided strong evidence that the photons really came from virtual particle pairs. The number of photons produced was extremely small, only a few per second, but their detection represented a breakthrough in understanding vacuum fluctuations. For the first time, scientists had directly observed the conversion of virtual particles into real ones through purely quantum mechanical processes. Similar experiments have since created photons using mechanical motion. Researchers have bounced laser beams off mirrors, vibrating at nearly 10% the speed of light. The moving mirrors gave energy to virtual photons, promoting them to real status. These photons carried away energy from the mirror's motion. Other laboratories have used rapidly rotating superconducting disks to generate photons from vacuum. The spinning motion created time-varying electromagnetic fields that could energize virtual particles. Again, real photons appeared, where quantum field theory predicted they would. These vacuum photon experiments probe the boundary between virtual and real particles. Virtual particles that exist for extremely brief periods can become real particles if they gain enough energy before disappearing. The energy can come from moving boundaries, changing fields, or other dynamic processes. The dynamic Casimir effect has practical applications in quantum technology. It provides a way to generate entangled photon pairs on demand for quantum computing and communication systems. It also offers insights into how quantum fields behave near rapidly moving boundaries. Some researchers speculate that the dynamic Casimir effect might operate, but the energy hidden in quantum vacuum pales in comparison to what astronomers have discovered in the vast emptiness between galaxies. The Boötes void stretches across 330 million light-years of space, but contains only 60 known galaxies in a volume that should hold 10,000. This cosmic desert represents one of the largest known structures in the universe. Most of its volume appears completely empty, with galaxy densities less than 1/10 the cosmic average. Yet even this seemingly barren region isn't truly empty but filled with invisible phenomena that shape cosmic evolution. Cosmic voids form the dominant feature of the universe's large-scale structure. They occupy about 80% of the total volume of space, despite containing only a tiny fraction of visible matter. These enormous bubbles separate the cosmic web's filaments, where most galaxies cluster together. Think of the universe like a vast soap bubble foam. The soap films represent galaxy filaments and clusters where matter concentrates. The air inside each bubble represents cosmic voids where very little visible matter exists. But just as soap bubbles aren't truly empty of air, cosmic voids aren't truly empty of matter and energy. Dark matter threads through cosmic voids in incredibly sparse concentrations. While galaxy clusters might contain hundreds of times more dark matter than average, voids contain only about 15% of the mean cosmic density. This dark matter forms extremely tenuous webs that connect distant galaxies across void spaces. Cosmic microwave background radiation fills every cubic centimeter of void space. This ancient light from the early universe carries virtually no energy, but provides a uniform glow throughout the cosmos. No matter how empty a void appears, this fossil radiation from the Big Bang passes through it continuously. Magnetic fields permeate cosmic voids with strengths at least 10 trillion times weaker than Earth's magnetic field. These fields might have formed in the early universe or been generated by jets from distant galaxies. Despite their weakness, they influence the motion of charged particles across cosmic scales. Neutrinos stream through void spaces at nearly the speed of light. These ghostly particles interact so weakly with matter that they pass through entire planets without stopping. Cosmic voids provide the least obstructed paths for neutrinos traveling between distant sources and detectors on Earth. High-energy cosmic rays cross void spaces during their journeys from distant sources. These particles carry energies millions of times higher than anything produced in human-made accelerators. Voids offer relatively clear paths for cosmic rays, though even the sparse matter in voids can deflect or absorb the highest energy particles. Gravitational waves from merging black holes and neutron stars propagate through void spaces at the speed of light. These ripples in space-time itself encounter minimal matter to interfere with their passage. Cosmic voids provide the clearest windows for detecting gravitational wave signals from the distant universe. Dark energy dominates the matter-energy content of cosmic voids. This mysterious component makes up about 70% of the universe's total energy density and drives cosmic expansion. In dense regions like galaxy clusters, dark energy's effects are overwhelmed by gravity, but in voids, dark energy reigns supreme. The expansion of cosmic voids provides clues about dark energy's nature. Voids expand faster than denser regions of space because they contain less matter to resist dark energy's repulsive effect. Measuring void expansion rates helps astronomers constrain dark energy's properties and cosmic evolution. Some theories propose that cosmic voids themselves generate dark energy through quantum effects in extremely low-density regions. The expansion of voids might create new space faster than virtual particles can fill it, leading to observable effects on cosmic acceleration. Future space telescopes will map cosmic voids in unprecedented detail, revealing their internal structure and evolution. These observations could unlock secrets about dark energy, dark matter, and the fundamental nature of empty space itself. But even the sparse matter in cosmic voids seems crowded compared to the mysterious force that fills every point in space. Dark energy exerts enough repulsive pressure to overcome gravity across distances larger than 300 million light-years, forcing distant galaxies to accelerate away from each other. This invisible force makes up roughly 70% of everything that exists in the universe. Unlike matter and radiation that become diluted as space expands, dark energy maintains constant density everywhere. As the universe grows larger, more dark energy appears to fill the newly created space. Astronomers discovered dark energy by studying distant supernova explosions that appeared dimmer than expected. These cosmic lighthouses should have revealed a universe whose expansion was slowing down due to gravity. Instead, they showed that cosmic expansion has been accelerating for the past 5 billion years. Think of dark energy like an invisible spring embedded in the fabric of space itself. The more you stretch the spring, the harder it pushes back. As the universe expands, dark energy's repulsive force grows stronger, accelerating the expansion even faster. This creates a runaway process that could continue forever. Dark energy's effects become noticeable only across cosmic distances. Within our solar system, galaxy, or even local galaxy cluster, gravity completely overwhelms dark energy's influence. But across hundreds of millions of light-years, dark energy's cumulative push becomes stronger than gravitational attraction. The local group of galaxies, including our Milky Way and the Andromeda Galaxy, remains gravitationally bound despite dark energy. These galaxies will continue moving toward each other and eventually merge in about 4 billion years. Dark energy affects only the largest cosmic structures. Different theories attempt to explain dark energy's origin. The cosmological constant model treats it as an inherent property of empty space itself. Quintessence models propose that a dynamic field pervades the universe and drives acceleration. Alternative theories modify gravity's behavior on cosmic scales. The cosmological constant represents the simplest dark energy model. It assumes that empty space has a fixed energy density that never changes. This energy creates negative pressure that drives cosmic expansion. Einstein originally proposed a cosmological constant to balance gravity in a static universe. Quintessence models involve scalar fields that can change over time and space. These fields behave like the Higgs field, but operate on cosmic scales instead of subatomic ones. Quintessence could explain why dark energy's effects became dominant only recently in cosmic history. Modified gravity theories propose that Einstein's general relativity breaks down on the largest scales. These theories predict that gravity becomes repulsive rather than attractive across cosmic distances. They attempt to explain dark energy without invoking new forms of matter or energy. Dark energy's precise nature remains one of physics' greatest mysteries. It doesn't interact with electromagnetic radiation, making direct detection impossible. Scientists must infer its properties from its gravitational effects on cosmic expansion and structure formation. The amount of dark energy seems perfectly tuned to allow complex structures like galaxies and stars to form. If dark energy were much stronger, it would have prevented matter from clumping together in the early universe. If it were much weaker, the universe might have collapsed before life could develop. Future space missions will measure dark energy's properties with unprecedented precision. The Nancy Grace Roman Space Telescope will observe millions of galaxies to track how dark energy affects cosmic expansion over time. These measurements could reveal whether dark energy changes or remains constant. Dark energy's dominance ensures that the universe's far future will be cold, dark, and empty. Galaxy clusters will become isolated islands, separated by ever-growing voids. Eventually, dark energy might tear apart galaxies, stars, and even atoms in a scenario called the Big Rip. But in extreme environments around neutron stars, even stronger forces than dark energy reshape the very structure of empty space. The magnetic field around a neutron star reaches strengths of 1 trillion Tesla, powerful enough to bend quantum vacuum fluctuations and create detectable changes in light passing through empty space. These cosmic lighthouses pack more mass than our Sun into a sphere only 12 miles across. Their surfaces experience gravity 600 billion times stronger than Earth's, but their magnetic fields represent the most extreme force in the known universe, reshaping the fundamental properties of space itself. Neutron star magnetic fields arise from the collapse of massive stars during supernova explosions. As the star's core contracts, magnetic field lines become compressed and twisted into incredibly concentrated knots. The resulting field strength exceeds anything achievable in human laboratories by factors of millions. Think of these magnetic fields like invisible highways that force charged particles to travel in specific directions. Near neutron stars, electrons and protons must follow magnetic field lines that spiral around the star's surface. This creates beams of radiation that sweep across space like lighthouse beams. The quantum vacuum responds to these extreme magnetic fields through a phenomenon called vacuum birefringence. Virtual electron-positron pairs in the vacuum become polarized by the magnetic field, slightly changing how light waves propagate through empty space. Different polarizations of light travel at slightly different speeds. This effect splits unpolarized light into two beams with perpendicular polarizations, similar to how certain crystals split light beams. The splitting happens in apparently empty space because virtual particles in the quantum vacuum act like an optical medium. Strong magnetic fields turn the vacuum itself into a type of lens. Astronomers have detected vacuum birefringence around neutron stars using X-ray telescopes. Light from the neutron star's hot surface becomes polarized as it passes through the magnetized vacuum near the star. The polarization patterns match theoretical predictions for quantum vacuum effects in strong magnetic fields. These observations provide direct evidence that virtual particles really exist and affect physical processes. The quantum vacuum isn't just a mathematical construct, but represents genuine fluctuations in electromagnetic fields that can be influenced by external forces. Neutron star magnetic fields also accelerate particles to incredible energies. Electrons captured by the field can reach speeds within 1 part in a billion of light speed. These relativistic electrons create synchrotron radiation that glows across the electromagnetic spectrum, from radio waves to gamma rays. The magnetic field funnels this radiation into narrow beams that emerge from the neutron star's magnetic poles. As the star rotates, these beams sweep across space like lighthouse beams. If Earth happens to lie in the beam's path, we detect regular pulses of radiation and call the object a pulsar. pulsar timing provides the most precise measurements of rotation and magnetic field properties. Some pulsars maintain timing accuracy better than atomic clocks, allowing astronomers to detect tiny changes in their magnetic fields and rotation rates over decades of observation. The strongest neutron star magnetic fields might approach the critical field strength, where virtual particles can become real. At field strengths near 10 to the 13th Tesla, virtual electron-positron pairs could gain enough energy to materialize as real particles. This would create matter from pure electromagnetic energy. Such extreme field strengths might exist in magnetars, a special class of neutron stars with the strongest known magnetic fields. These objects occasionally produce enormous magnetic field eruptions that release more energy in seconds than our Sun produces in years. Future X-ray telescopes will study vacuum birefringence effects around many neutron stars, providing detailed maps of their magnetic field structures. These observations will test quantum electrodynamics under the most extreme conditions possible. But even neutron star magnetic fields seem weak compared to the reality warping effects that occur near black holes. The intense gravitational field near a black hole's event horizon can separate virtual particle pairs before they annihilate, causing one partner to fall into the black hole while the other escapes as real radiation. This process, predicted by Stephen Hawking in 1974, demonstrates how extreme gravity can convert quantum vacuum fluctuations into observable particles. Black holes actually glow with thermal radiation, despite their reputation for absorbing everything that approaches them. Virtual particle pairs constantly appear throughout space, including near black hole event horizons. Normally, these pairs annihilate each other almost immediately, returning their borrowed energy to the quantum vacuum. But the extreme gravitational field near a black hole can disrupt this process. Think of virtual particles like cosmic twins connected by an invisible rope. Usually, the rope pulls them back together before they can escape. But near a black hole, one twin might fall past the point of no return, while the other gets pulled away by the intense gravitational field. The rope breaks, and both particles become real. The escaping particle carries away positive energy, while its partner falls into the black hole with negative energy. This energy bookkeeping ensures that the black hole loses mass equal to the energy carried away by Hawking radiation. Larger black holes have weaker gravitational fields near their horizons and emit less radiation. Hawking radiation has a perfect thermal spectrum determined by the black hole's surface gravity. Stellar mass black holes have incredibly low temperatures, less than 1/1,000,000th of a degree above absolute zero. Supermassive black holes are even colder, with temperatures measured in billionths of a degree. These temperatures make Hawking radiation virtually impossible to detect from natural black holes. The cosmic microwave background radiation is much warmer than Hawking radiation from any realistic black hole. The radiation would be completely overwhelmed by thermal noise from the surrounding environment. But Hawking radiation has profound theoretical implications. It suggests that black holes have finite lifetimes and will eventually evaporate completely. Smaller black holes evaporate faster than larger ones, with evaporation rates inversely proportional to the square of their mass. A black hole with our Sun's mass would take longer than the age of the universe raised to the 64th power to evaporate completely. Supermassive black holes would take even longer, but primordial black holes formed in the early universe could be evaporating right now if they had the right initial mass. Primordial black holes with masses comparable to mountains would be completing their evaporation today after nearly 14 billion years. These black holes would explode in bursts of high-energy particles and gamma rays as they reach their final moments. Astronomers search for these explosive signatures. The Hawking process also leads to the black hole information paradox. Quantum mechanics requires that information cannot be destroyed, but Hawking radiation appears to be completely thermal with no information content. If black holes evaporate completely, where does the information that fell into them go? Various solutions have been proposed, including the idea that information is encoded in subtle correlations within Hawking radiation. Alternative theories suggest that black holes don't destroy information but transfer it to their event horizon surfaces or to baby universes connected by wormholes. Recent developments in quantum gravity suggest that the vacuum near black holes might be more complex than originally thought. Quantum entanglement between particles inside and outside the event horizon could preserve information while maintaining the thermal nature of Hawking radiation. Laboratory experiments have created black hole analogues using fluid flow, light pulses, and ultra-cold gases. These systems can test aspects of Hawking radiation in controlled environments, though they don't reproduce the gravitational effects of real black holes. But the phenomena occurring near black holes represent just one example of how space itself participates in the creation of new matter and energy. Every second, the expansion of the universe creates roughly 10 to the 78 cubic meters of new space, more volume than all the atoms in the observable universe occupy. This space doesn't expand into anything else or push existing space aside. New space simply comes into existence everywhere simultaneously, stretching the distances between galaxies and galaxy clusters. The process violates no conservation laws because space itself isn't a conserved quantity. Cosmic expansion differs fundamentally from ordinary explosions that blast matter through existing space. During expansion, space itself grows larger, while galaxies remain essentially the same size. Think of galaxies like dots drawn on a balloon that's being inflated. The dots don't expand, but the distance between them increases as new balloon material appears. General relativity predicts that space can be created or destroyed depending on the matter and energy it contains. Positive energy density, like that from ordinary matter and radiation, tends to curve space in ways that slow expansion. Negative pressure, like that from dark energy, causes space to expand faster. The Friedmann equations describe how space expands based on its energy content. These equations treat space as a dynamic quantity that responds to the matter and energy within it. Unlike Newton's laws that assume space is fixed and unchanging, general relativity allows space to evolve over time. During cosmic inflation in the early universe, space expanded at exponential rates that created enormous volumes in tiny fractions of seconds. A region smaller than an atomic nucleus grew to larger than a basketball in less than 10 to the negative 30 seconds. This inflation generated virtually all the space in our observable universe. The amount of space created during inflation staggers comprehension. If inflation lasted for just 60 e-folding times, a region with the Planck length grew to 10 to the 26 times larger. That's like expanding a single proton to larger than the solar system in an instant. Modern cosmic expansion continues creating new space, though at much slower rates than during inflation. The current expansion rate means that distances double approximately every 10 billion years. This gentle expansion will continue accelerating due to dark energy's influence. The creation of new space carries profound implications for energy conservation. If dark energy has constant density throughout space, then expanding space creates new dark energy. The universe's total dark energy content increases over time as more space comes into existence. This apparent violation of energy conservation puzzled physicists until they realized that gravitational fields can have negative energy. The negative gravitational energy exactly cancels the positive dark energy, maintaining overall energy conservation even as space expands. Some theories suggest that space creation could be harnessed for practical purposes. If the mechanism that drives cosmic expansion could be reproduced artificially, it might provide unlimited energy by creating new space filled with dark energy. However, no known physics allows such manipulation. The expansion of space also affects quantum vacuum fluctuations. As space expands, quantum fluctuation wavelengths get stretched along with the expansion. Some fluctuations that started as virtual particles during inflation became large enough to seed the formation of galaxies and cosmic structure. The accelerating expansion, driven by dark energy, will eventually create space faster than light can travel between distant galaxies. This cosmic event horizon will isolate galaxy clusters from each other, making most of the universe permanently unobservable from any given location. Future observations of cosmic expansion could reveal whether space creation follows currently understood laws or involves new physics. Precision measurements of dark energy's properties will determine whether space expansion continues forever or eventually reverses. But the creation of space during cosmic expansion pales in comparison to the space that might have been created during the universe's first moments. A random quantum fluctuation, smaller than an atomic nucleus, expanded to create a region larger than a grapefruit in less time than light takes to cross a proton. This inflationary epoch occurred during the universe's first tiny fraction of a second, when temperatures and energies exceeded anything that will ever exist again. A special scalar field called the inflaton drove exponential expansion that created virtually all the space in our observable universe from a microscopic quantum bubble. Inflation solves several puzzles about our universe's properties. The cosmic microwave background radiation has almost exactly the same temperature in all directions, even from regions that should never have been in thermal contact. Inflation explains this uniformity by expanding a small, thermal tiny bumps and valleys that later became the seeds for galaxy formation after inflation ended. During inflation, space doubled in size approximately every 10 to the negative 37 seconds. This doubling continued for at least 60 times, meaning the universe grew by a factor of at least 10 to the 18. Some inflation models allow much longer periods, with correspondingly larger expansion factors. The energy that powered inflation came from the inflaton field's potential energy. Like a compressed spring, the field contained enormous amounts of energy that got released when inflation ended. This energy eventually converted into the hot plasma of particles and radiation that filled the early universe. Inflation ended when the inflaton field rolled off its hilltop and began oscillating around the valley bottom. These oscillations decayed into ordinary particles through a process called reheating. The universe transitioned from cold, exponentially expanding space to hot, dense plasma filled with matter and radiation. The transition from inflation to normal expansion happened in less than 1 second after the Big Bang. By the time the universe was 1 second old, it had cooled enough for protons and neutrons to form stable nuclei. The rapid changes during these early moments set the stage for everything that followed. Inflation naturally explains why our universe contains exactly the right amount of matter to make it geometrically flat. The exponential expansion drove the universe toward flatness regardless of its initial curvature. Any curved space becomes indistinguishable from flat space when expanded by enormous factors. Quantum fluctuations during inflation created the primordial density variations that eventually grew into galaxies and galaxy clusters. These fluctuations had a nearly scale-invariant spectrum, meaning they had similar amplitudes across a wide range of size scales. This spectrum matches observations of cosmic microwave background anisotropies. Different inflation models make specific predictions about these primordial fluctuations. Some models predict detectable gravitational waves produced during inflation. Others predict non-Gaussian features in the cosmic microwave background that future observations might detect. Eternal inflation models suggest that inflation never completely ends, but continues in some regions while ending in others. This creates a multiverse with infinite numbers of pocket universes, each with potentially different physical laws and constants. Our observable universe represents just one bubble in this vast cosmic foam. If eternal inflation is correct, then quantum fluctuations continuously create new universes throughout space and time. The process that created our cosmos from a microscopic fluctuation continues operating on scales far beyond our observational reach. But inflation might not represent the most dramatic way that quantum fluctuations can reshape reality. A bubble of true vacuum nucleating anywhere in the universe would expand at 99.99% the speed of light, converting everything in its path to a cosmos with completely different laws of physics. This scenario represents perhaps the most dramatic way our universe could end or transform. Unlike gradual processes like heat, death, or big rip scenarios that take billions of years, false vacuum decay would rewrite reality faster than any warning signal could reach us. Current physics suggests our universe might exist in a metastable state called a false vacuum. Like a ball balanced precariously on a hilltop, our reality appears stable, but could suddenly roll into a deeper valley, representing the true vacuum state. The transition would release enormous amounts of energy and fundamentally alter physical constants. Think of false vacuum decay like a cosmic phase transition, similar to water freezing into ice. But instead of just changing from liquid to solid, the transition would change the basic rules that govern how particles interact. Electrons might cease to exist, or new forces might appear that make chemistry impossible. The Higgs field provides the most likely candidate for false vacuum decay in our universe. Measurements of the Higgs boson mass place it near the boundary between stability and instability. Small changes in the top quark mass or other parameters could push the Higgs field into a metastable configuration. If the Higgs field exists in a false vacuum, quantum tunneling could eventually trigger decay to the true vacuum state. A small region of space might randomly fluctuate into the lower energy configuration, creating a bubble of true vacuum that expands outward at nearly light speed. The bubble wall would carry enormous energy as it expanded. This energy could be equivalent to the mass of entire stars compressed into a surface thinner than atomic nuclei. Anything encountering the bubble wall would be instantly vaporized by energies far exceeding those in supernova explosions. Inside the bubble, physics would operate according to completely different rules. The electron mass might be different, or electrons might not exist at all. The strong nuclear force could have different strength, making atomic nuclei unstable. Even the number of spatial dimensions might change. Sidney Coleman and Frank DeLucia calculated in 1980 that false vacuum bubbles would immediately collapse gravitationally. The energy contained in the bubble wall would create such intense gravitational fields that the entire region would form a black hole. Not even the new physics inside could survive this gravitational collapse. The probability of false vacuum decay occurring in our cosmic neighborhood appears extraordinarily small. Standard model calculations suggest the lifetime of our current vacuum state exceeds 10 to the 100th years, far longer than the current age of the universe. We're not in immediate danger. However, high-energy processes might trigger false vacuum decay if they create conditions similar to those during cosmic inflation. Particle accelerator experiments, cosmic ray collisions, or black hole formation could potentially nucleate vacuum decay bubbles if our vacuum is truly metastable. Some physicists worry that future high-energy experiments might accidentally trigger vacuum decay. Each new energy frontier explored by particle accelerators probes conditions that have never existed since the early universe. Unknown physics at these energies could destabilize our vacuum state. Other theories suggest that false vacuum decay might be impossible due to unknown physics beyond the standard model. Supersymmetry, extra dimensions, or other theoretical frameworks could stabilize the Higgs field and prevent vacuum transitions. Only future experiments will determine which scenario is correct. If false vacuum decay does occur, it would represent the ultimate cosmic reset. All current structures would be erased and replaced by whatever physics operates in the true vacuum. Life, chemistry, and recognizable matter would cease to exist, replaced by entirely new forms of matter and energy. But false vacuum decay depends on a deeper question about the nature of empty space itself. Every cubic millimeter of apparently empty space contains enough Higgs field energy to equal the mass of about 1 billion protons. Yet this energy somehow remains completely invisible. The Higgs field permeates the entire universe, like an invisible ocean that gives mass to fundamental particles. Without this field, electrons, quarks, and other particles would be massless and travel at the speed of light. Matter as we know it could not exist. Unlike other quantum fields that fluctuate around zero values in empty space, the Higgs field maintains a constant, non-zero value everywhere. This value, called the vacuum expectation value, determines the masses of particles that interact with the field. Stronger interactions produce heavier particles. Think of the Higgs field like thick syrup filling all of space. Particles that interact strongly with the syrup move slowly and appear heavy. Particles that barely interact with the syrup move quickly and appear light. Photons don't interact with the Higgs field at all, so they remain massless and travel at light speed. The Higgs mechanism operates through spontaneous symmetry breaking. In the early universe, at extremely high temperatures, the Higgs field had zero value and all particles were massless. As the universe cooled, the field spontaneously acquired its current non-zero value, giving mass to particles through their interactions with it. This symmetry breaking resembles a pencil balanced on its point. The balanced position has perfect symmetry, but it's unstable. Any tiny disturbance causes the pencil to fall in some random direction, breaking the symmetry. The Higgs field, similarly, fell into its current configuration when the universe cooled sufficiently. The discovery of the Higgs boson in 2012 confirmed that the Higgs field exists. The Higgs boson represents excitations in the Higgs field, like waves on the ocean's surface. Creating these excitations requires enormous energies available only in powerful particle accelerators. Higgs boson decay patterns reveal how the field interacts with different particles. Heavier particles couple more strongly to the Higgs field, so Higgs bosons decay into heavy particles more often than light ones. These decay ratios match theoretical predictions precisely. The Higgs field's energy density creates a cosmological mystery. Quantum field theory predicts that the field should contribute enormously to the universe's total energy density. This contribution should cause space to expand much faster than observed. Yet somehow the Higgs field's energy seems to have no gravitational effect. Some mechanism must cancel the Higgs field's gravitational influence while preserving its role in giving mass to particles. Supersymmetry provides one possible solution by introducing partner particles that cancel the Higgs field's vacuum energy. Other theories invoke extra dimensions or modified gravity. The Higgs field could exist in multiple vacuum states with different energy densities. Our current vacuum might not represent the lowest possible energy state, making it a false vacuum that could decay to a true vacuum with different particle masses and forces. Measurements of Higgs boson properties determine whether our vacuum is stable, metastable, or unstable. Current data suggests we live in a metastable vacuum that could eventually decay but has an extremely long lifetime. The precise stability depends on unmeasured parameters like the top quark's exact mass. Future particle accelerators will measure Higgs properties with greater precision, narrowing the allowed ranges for vacuum stability. These measurements will determine whether our universe will exist indefinitely or eventually undergo a phase transition to different physics. The Higgs field also influences cosmic evolution through its interactions with other fields during inflation. Fluctuations in the Higgs field during the early universe might have contributed to the density variations that became galaxies and cosmic structures. But the question of vacuum stability leads to an even more fundamental concern about the nature of existence itself. A transition from false vacuum to true vacuum would not only destroy all existing matter, but could rewrite the fundamental constants that determine how particles interact, making our current laws of physics obsolete. This ultimate phase transition would represent the most complete possible destruction and recreation of reality. Unlike other cosmic catastrophes that destroy structures while preserving basic physics, vacuum decay would eliminate the very rules that govern atomic and molecular behavior. The standard model of particle physics contains 19 fundamental constants that determine particle masses, force strengths, and interaction probabilities. In a true vacuum state, these constants could have completely different values, or additional constants might appear for new types of particles and forces. Imagine if the electromagnetic force suddenly became 10 times stronger or 100 times weaker. Atoms would either collapse under excessive electrical attraction or fly apart because electrons couldn't remain bound to nuclei. Either way, chemistry as we know it would become impossible. Changes in the strong nuclear force would have equally devastating effects. If the strong force became too weak, atomic nuclei would disintegrate into individual protons and neutrons. If it became too strong, protons might fuse together uncontrollably, creating exotic forms of nuclear matter. The electron mass represents another critical parameter. In a different vacuum state, electrons might be much heavier or lighter than in our universe. Heavy electrons would create tiny atoms with completely different chemical properties. Light electrons might not form stable atoms at all. New particles could exist in the true vacuum that have no analog in our current physics. These particles might carry exotic charges or interact through completely new forces. The particle physics of the true vacuum could be as different from ours as our physics is from that of a universe with no particles at all. Even more fundamentally, space and time might have different properties in the true vacuum. The number of spatial dimensions could change from 3 to some other value. Time might flow differently or have a discrete rather than continuous structure. Gravity itself might operate through entirely different mechanisms. The transition process would obliterate all existing structures before the new physics could create replacements. Atoms would disintegrate as their binding energies changed. Molecular bonds would break as electromagnetic forces shifted. Complex structures like stars, planets, and living organisms would dissolve instantly. The energy released during vacuum decay could exceed the binding energy of atomic nuclei by enormous factors. This energy would heat matter to temperatures far exceeding those in stellar cores, vaporizing everything into a plasma of elementary particles that would then transform according to the new physics. Even fundamental concepts like causality and locality might change in the true vacuum. Events that require causes in our universe might happen spontaneously. Particles that cannot travel faster than light might move instantaneously across arbitrary distances. The very logic of physical law could be different. Some theoretical models suggest that vacuum decay might create baby universes with the new physics, rather than transforming our existing space. The decay bubble might pinch off from our universe and form a separate cosmos with different physical laws, leaving our universe unchanged. Other models propose that consciousness or information might somehow survive vacuum decay by transferring to substrates based on the new physics. This speculative possibility remains far beyond current scientific understanding and might violate fundamental principles of information theory. The probability of vacuum decay remains uncertain because it depends on physics beyond the standard model that hasn't been experimentally tested. String theory, supersymmetry, extra dimensions, or other theoretical frameworks could make vacuum decay impossible or inevitable. But regardless of whether our vacuum is truly stable or merely long-lived, the very possibility of vacuum decay reveals how precarious our existence might be, balanced on the edge between order and chaos in ways we're only beginning to understand. German physicists detected quantum vacuum fluctuations directly by measuring tiny variations in laser light after it passed through a crystal, proving that empty space really does buzz with invisible activity. This breakthrough experiment used extraordinarily sensitive instruments to observe the quantum vacuum's effect on real photons. The researchers sent precisely controlled laser pulses through a special crystal and measured how the vacuum's quantum fluctuations randomly changed the light's polarization. Think of this measurement like trying to detect ocean waves by watching how they rock a floating cork. The quantum vacuum fluctuations represent invisible waves that slightly disturb any light passing through them. By measuring these tiny disturbances, scientists can map the vacuum's hidden activity. The experiment required cooling, superconducting circuits to temperatures colder than outer space. At these extreme temperatures, thermal vibrations nearly disappear, allowing scientists to detect the much smaller quantum fluctuations. Any heat would overwhelm the delicate vacuum signals they were trying to measure. The laser pulses lasted only femtoseconds, 1,000,000 times shorter than the blink of an eye. These ultra-short pulses probe vacuum fluctuations happening on the smallest possible timescales. Longer pulses would average out the fluctuations, hiding the vacuum's rapid oscillations. Each measurement detected variations smaller than 1 part in a billion. The vacuum fluctuations changed the laser light's properties by amounts so tiny that only the most sensitive instruments could detect them. These changes proved that quantum fields really do fluctuate, even in apparently empty space. The crystal used in the experiment acts like a quantum converter that transforms vacuum fluctuations into measurable signals. Virtual particles in the vacuum slightly change the crystal's optical properties, which then affects how light travels through it. The crystal amplifies these microscopic effects into detectable changes. Similar experiments have used superconducting quantum interference devices to measure vacuum fluctuations in magnetic fields. These squids can detect magnetic field changes smaller than those produced by a single electron spinning a mile away. They reveal that vacuum fluctuations occur in every type of quantum field. Other laboratories have measured vacuum fluctuations using trapped atoms as ultrasensitive detectors. Individual atoms respond to vacuum field variations by slightly changing their energy levels. Precision spectroscopy can measure these tiny energy shifts and map the vacuum's invisible structure. These direct measurements confirm theoretical predictions about quantum vacuum behavior. The observed fluctuation patterns match exactly what quantum field theory predicted decades before experimental technology became sensitive enough to detect them. Reality operates according to quantum mechanical principles even in empty space. The ability to measure vacuum fluctuations opens new possibilities for fundamental physics research. Scientists can now study how vacuum properties change near different materials, in strong electromagnetic fields, or under extreme conditions. These studies probe the deepest levels of physical reality. Future experiments might detect even subtler vacuum effects, such as fluctuations in gravitational fields or changes in the fabric of space-time itself. These measurements could reveal new physics beyond the standard model and test theories of quantum gravity. Some researchers speculate that precisely controlling vacuum fluctuations might enable new technologies. If scientists could manipulate the quantum vacuum the way they manipulate electromagnetic fields, it might lead to revolutionary advances in energy generation, computation, or communication. But even these remarkable laboratory measurements pale in comparison to the ancient radiation that has been soaking every point in space for nearly 14 billion years. Every cubic centimeter of the universe contains about 400 photons of cosmic microwave background radiation left over from when the cosmos was only 380,000 years old and hot enough to melt steel. This ancient light fills every corner of space with a nearly uniform glow that represents the oldest observable phenomenon in the universe. The radiation carries information about cosmic conditions when the first atoms formed, and space became transparent for the first time. Before this cosmic dawn, the universe existed as a hot, dense plasma where electrons and protons flew around freely. Photons could travel only tiny distances before colliding with free electrons, making space completely opaque like the inside of a thick fog. Light couldn't propagate across cosmic distances. As the universe expanded and cooled, temperatures dropped below 3,000 degrees Kelvin. At this critical temperature, electrons combined with protons to form neutral hydrogen atoms. Suddenly, photons could travel freely across space without constantly hitting free electrons. Think of this transition like fog lifting to reveal a clear morning sky. The moment atoms formed, space became transparent, and light could stream freely in all directions. The photons we detect today, as cosmic microwave background radiation began their journey at that precise moment. These ancient photons have been traveling through space for nearly 14 billion years. Cosmic expansion has stretched their wavelengths from visible light into microwaves, cooling them from thousands of degrees to just 2.7 degrees above absolute zero. They've become the coldest things in the observable universe. The cosmic microwave background provides our most direct view of the universe when it was 1,000 times smaller and 1 billion times denser than today. The tiny temperature variations across the sky reveal the seeds that eventually grew into galaxies, galaxy clusters, and the cosmic web we observe today. Precision measurements show that the background radiation has almost exactly the same temperature in all directions, varying by only about 1 part in 100,000. This remarkable uniformity poses puzzles about how widely separated regions could have the same temperature without ever being in contact. The radiation's near-perfect uniformity supports cosmic inflation theory. During inflation, a small region with uniform temperature expanded to fill the entire observable universe. This explains why opposite sides of the sky have nearly identical temperatures despite being too far apart to exchange heat. Subtle patterns in the temperature variations encode information about the universe's geometry with unprecedented precision. These measurements could detect gravitational waves produced during cosmic inflation, providing direct evidence for the rapid expansion that occurred in the universe's first moments. The cosmic microwave background represents the universe's baby picture, showing conditions when space was young, hot, and simple. Every point in space still glows with this ancient light, carrying messages from an era when the first atoms were just beginning to form. But hidden beneath this ancient glow lies an even more fundamental source of energy that makes the background radiation seem almost insignificant. Theoretical calculations suggest that every cubic meter of empty space contains zero-point energy, equivalent to about 10 trillion joules, enough to instantly vaporize all water on our planet. This staggering energy density comes from quantum field fluctuations that can never be eliminated, even at absolute zero temperature. Every quantum field throughout space maintains minimum oscillations that contribute to an enormous total energy content that somehow remains hidden from direct observation. Zero-point energy arises because quantum mechanics forbids any system from having exactly zero energy. Every harmonic oscillator, whether a vibrating atom or a quantum field mode, must have at least 1/2 unit of quantum energy, even in its lowest possible state. Since space contains infinite numbers of field modes, the total energy becomes infinite. Think of zero-point energy like the minimum heartbeat of reality that can never stop beating. Just as your heart maintains a baseline rhythm even during rest, quantum fields maintain baseline vibrations even in perfect emptiness. These vibrations represent the universe's fundamental restlessness. Physicists calculate zero-point energy by adding up contributions from all possible quantum field oscillations at every point in space. Each electromagnetic field mode contributes energy proportional to its frequency. Higher frequency modes carry more energy, and there's no upper limit to possible frequencies. The energy density grows without bound as you include higher frequency modes. Cutting off the calculation at the Planck frequency gives energy densities around 10 to the 113th joules per cubic meter. This exceeds the energy density of atomic nuclei by about 60 orders of magnitude. If zero-point energy could be extracted, a coffee cup's worth would power human civilization for millions of years. A cubic meter would contain more energy than our sun produces in its entire 10 billion year lifetime. The energy in a single room could move planets or create new stars. Yet, despite these enormous theoretical predictions, zero-point energy appears to have almost no observable effects on large-scale physics. The universe's expansion rate suggests a vacuum energy density about 10 to the -9 joules per cubic meter, making theoretical predictions wrong by over 120 orders of magnitude. This enormous discrepancy represents physics' worst theoretical failure. No other scientific prediction has ever been this spectacularly incorrect. The disagreement suggests that our understanding of quantum fields, gravity, or both, contains fundamental errors that need revolutionary corrections. Some theories propose that zero-point energy doesn't contribute to gravity because of unknown cancellation mechanisms. Supersymmetry could provide such cancellations by introducing partner particles with negative contributions that exactly cancel positive zero-point energies from known particles. Other theories suggest that space and time have different properties at the smallest scales that prevent infinite energy densities from occurring. String theory, loop quantum gravity, and other quantum gravity approaches attempt to resolve the zero-point energy problem through modified space-time structures. Despite theoretical difficulties, zero-point energy produces measurable effects in atomic and molecular physics. The Casimir effect, Lamb shift, and anomalous magnetic moments of particles all result from zero-point fluctuations. These effects can be calculated and measured with extraordinary precision. Entrepreneurs have proposed devices to extract energy from quantum vacuum fluctuations. These zero-point energy machines claim to harvest power from the quantum vacuum without violating conservation laws. However, thermodynamics forbids extracting net energy from systems in their lowest energy state. The zero-point energy problem highlights the deepest mysteries in fundamental physics. It connects quantum mechanics, general relativity, and cosmology in ways that current theories cannot adequately explain. Resolving this problem might require revolutionary advances in our understanding of space, time, and matter. But the zero-point energy problem represents just one example of how quantum vacuum calculations lead to absurd results. The theoretical prediction for vacuum energy density exceeds observational measurements by 1 followed by 120 zeros, making it the most inaccurate calculation in the history of science. This catastrophic disagreement between theory and observation suggests that either quantum field theory or general relativity contains fundamental errors. No other scientific theory has ever produced predictions that are wrong by such enormous factors while remaining successful in other areas. The problem begins with calculating how quantum fields contribute to the energy density of empty space. Every quantum field mode throughout the universe contributes zero-point energy that adds up to give the total vacuum energy. This energy should curve spacetime and affect cosmic expansion according to Einstein's general relativity. Naive calculations give vacuum energy densities around 10 to the 64th grams per cubic centimeter. This exceeds the density of atomic nuclei by 40 orders of magnitude. Space itself would be denser than the most compact matter in the universe, making atoms seem like thin wisps of vapor. More sophisticated calculations that include all known particles and fields give even larger values. The vacuum energy density reaches 10 to the 96th grams per cubic centimeter when calculated using quantum field theory's standard methods. This makes the original estimate seem conservative by comparison. Think of this like predicting that a feather weighs as much as a blue whale, then discovering your calculation was actually off by another 30 orders of magnitude. The vacuum energy prediction isn't just wrong, it's wrong by amounts that seem to transcend the boundaries of reasonable error. Observational astronomy provides tight constraints on vacuum energy density through measurements of cosmic expansion. The acceleration of cosmic expansion suggests vacuum energy densities around 10 to the negative 26 grams per cubic centimeter. This includes dark energy and any contributions from quantum vacuum fluctuations. The disagreement between theory and observation spans 120 orders of magnitude. To put this in perspective, the ratio between the size of a proton and the observable universe is only about 40 orders of magnitude. The vacuum energy discrepancy represents a much larger mismatch than any scale difference in nature. Some physicists argue that zero-point energy shouldn't contribute to gravity because it represents the lowest possible energy state. They propose that only energy differences above the vacuum state should curve spacetime. This approach reduces the theoretical prediction, but doesn't eliminate the discrepancy entirely. Supersymmetry provides another potential solution by introducing particles that cancel the vacuum energy contributions of known particles. For every fermion that contributes positive vacuum energy, supersymmetry predicts a boson that contributes equal negative energy. Perfect cancellation would eliminate the vacuum catastrophe completely. Unfortunately, supersymmetry must be broken in our universe because superpartners have not been observed despite extensive searches. Broken supersymmetry provides only partial cancellation, leaving vacuum energy densities still many orders of magnitude too large compared to observations. Alternative approaches modify general relativity to make it less sensitive to vacuum energy contributions. These modified gravity theories change how energy curves spacetime, potentially allowing large vacuum energies to exist without affecting cosmic expansion. However, most such modifications conflict with other observational tests. String theory attempts to resolve the vacuum catastrophe through extra dimensions and modified spacetime structures. In some string models, vacuum energy gets distributed across higher dimensions where it doesn't affect four-dimensional spacetime curvature. Other models invoke anthropic selection effects in multiverse scenarios. The vacuum catastrophe motivates searches for completely new physics beyond the standard model. Revolutionary changes in our understanding of quantum mechanics, gravity, or both might be necessary to explain why vacuum energy appears to have no gravitational effects. This fundamental problem connects to questions about the nature of space, time, and existence itself. Resolving the vacuum catastrophe could lead to breakthrough discoveries about reality's deepest principles, but even more disturbing possibilities emerge when considering how new universes might spontaneously appear from quantum fluctuations. Quantum tunneling events could spontaneously create bubbles of spacetime with completely different fundamental constants, particle types, and physical laws that expand into full universes with their own unique realities. This process, called bubble nucleation, represents the ultimate expression of quantum uncertainty applied to the structure of space and time itself. Just as virtual particles can tunnel through energy barriers to become real, entire universes might tunnel into existence from quantum vacuum fluctuations. Eternal inflation theory predicts that bubble nucleation occurs continuously throughout a vast multiverse. While inflation ended in our cosmic neighborhood 14 billion years ago, it continues forever in other regions, occasionally spawning new bubble universes with different physical properties. Each bubble universe begins as a microscopic quantum fluctuation that expands exponentially during its own inflationary epoch. The physics inside each bubble depends on how quantum fields settle into their vacuum states during the transition from inflation to normal expansion. Different settling patterns create different physics. Think of bubble nucleation like soap bubbles forming in boiling water. Each bubble starts tiny and grows rapidly, but the conditions inside each bubble can vary. Some bubbles might have different temperatures, pressures, or chemical compositions, depending on exactly how they formed. The fundamental constants that determine particle masses and force strengths could vary dramatically between bubble universes. One universe might have electrons 10 times heavier than in ours, making atoms completely different. Another might have stronger nuclear forces that prevent hydrogen from existing. Even the number of spatial dimensions could differ between bubbles. Our universe has 3 spatial dimensions plus time, but other bubbles might have 2, 4, or even hundreds of spatial dimensions. The geometry of space itself might follow different mathematical rules. Some bubble universes might contain types of matter that don't exist in our cosmos, Particles with exotic properties like fractional electric charges, magnetic monopoles, or stable forms of antimatter could dominate the physics in other bubbles. These particles might interact through forces unknown in our universe. The rate of bubble nucleation depends on the energy barriers between different vacuum states. High barriers make nucleation extremely rare, while low barriers allow frequent bubble creation. Current estimates suggest that bubble nucleation happens approximately once per cubic Hubble volume per Hubble time. Most newly nucleated bubbles would be sterile environments, incapable of supporting complex structures. Random values of fundamental constants would likely produce universes where atoms can't form, stars can't shine, or space itself is unstable. Life-supporting universes might be extraordinarily rare. The boundaries between bubble universes expand at nearly the speed of light. If another bubble's boundary ever reached our cosmic neighborhood, it would instantly convert our region to the new bubble's physics. Everything we know would cease to exist as new physical laws took effect. However, the ongoing expansion of space makes collisions between widely separated bubbles increasingly unlikely. Dark energy's acceleration ensures that distant bubbles move away from us faster than their boundaries can approach. We might be permanently isolated from other bubble universes. Some theories propose that baby universe creation occurs not just through inflation, but also through black hole formation. When matter collapses to form a black hole, the extreme conditions might nucleate a new bubble universe connected to ours through the black hole's interior. These baby universes would begin with physical constants, slightly different from those in their parent universe. Over time, a vast family tree of related universes could develop, each branching into new bubbles with modified physics. Our universe might be just one branch in this cosmic evolutionary process. Bubble nucleation represents the ultimate creativity of quantum mechanics. The same uncertainty that allows virtual particles to briefly exist might continuously create entire universes with unlimited varieties of physical laws. Reality becomes an infinite laboratory, exploring every possible way that matter and energy can behave. But the quantum processes that might create new universes also raise profound questions about the nature of time itself. Some theoretical physicists propose that time doesn't exist at the most fundamental level, but emerges from correlations between quantum vacuum fluctuations, making temporal flow an illusion created by quantum entanglement patterns. This radical idea suggests that the flow of time we experience results from how quantum information becomes organized rather than from any fundamental temporal dimension. At the deepest level of reality, only quantum correlations exist in a timeless state from which the appearance of time emerges. The Wheeler-DeWitt equation, which attempts to describe quantum gravity, contains no time parameter. In quantum gravity, the universe exists in a superposition of all possible configurations simultaneously. Time appears only when we measure specific quantum correlations between different parts of the cosmic wave function. Think of time like a story that emerges from reading random letters. Individual letters have no temporal sequence, but when organized correctly, they create narratives with clear beginnings, middles, and ends. Quantum vacuum fluctuations might provide the random letters that get organized into the story we experience as time. Quantum entanglement between vacuum fluctuations could create the illusion of temporal sequence. When widely separated regions of space share entangled quantum states, measuring one region instantly affects the other. These correlations might define what we perceive as simultaneous events across space. The second law of thermodynamics usually explains time's apparent direction through increasing entropy. But in quantum gravity, entropy might not be fundamental either. Instead, the apparent increase in entropy could result from how quantum information becomes distributed among entangled vacuum fluctuations. Loop quantum gravity suggests that space and time have discrete, granular structures at the Planck scale. Time might consist of individual temporal atoms that connect to each other through quantum processes. The smooth flow of time we experience would emerge from these underlying discrete jumps. Causal set theory proposes that space-time consists of discrete events connected by causal relationships. Time emerges from the partial ordering of these events, rather than from any continuous temporal dimension. Quantum vacuum fluctuations might represent the fundamental events from which causal structures develop. Some interpretations of quantum mechanics suggest that time branches into multiple streams, corresponding to different measurement outcomes. In this view, vacuum fluctuations continuously split the timeline into parallel branches, creating a tree-like structure of temporal flow rather than a single time dimension. The holographic principle implies that all information in a volume of space can be encoded on its boundary surface. Time might be a holographic projection that emerges when three-dimensional information gets encoded on two-dimensional quantum vacuum states at the cosmic boundary. Emergent time theories make testable predictions about cosmic microwave background radiation patterns. If time emerges from quantum correlations, these correlations might leave detectable signatures in the universe's earliest observable light. Future precision measurements could test whether time is fundamental or emergent. The emergence of time from timeless quantum correlations parallels how consciousness might emerge from unconscious neural processes. Neither time nor consciousness appear to exist at the most fundamental level, yet both emerge from complex correlations in underlying quantum or neural networks. If time is emergent rather than fundamental, it raises profound questions about the nature of existence. What does it mean for events to happen if time itself doesn't exist at the deepest level? How can cause and effect operate in a timeless quantum reality? Some philosophers argue that emergent time theories support the idea that past, present, and future are equally real. From the timeless perspective of quantum gravity, all moments exist simultaneously in the cosmic wave function. Our perception of temporal flow reflects our limited ability to access this complete quantum information. These ideas suggest that time travel might be possible in principle, since all temporal locations exist simultaneously in the underlying quantum state. However, practical time travel would require manipulating quantum correlations on cosmic scales, far beyond any conceivable technology. The question of whether time is fundamental or emergent connects to the deepest mysteries about consciousness, free will, and the nature of reality. If time emerges from quantum vacuum fluctuations, then the temporal dimension that seems most basic to our experience might be the most illusory. But these speculations about the fundamental nature of time pale in comparison to how precariously balanced our entire reality might be. Current measurements place our universe's vacuum state precisely at the boundary between eternal stability and inevitable decay, like a pencil perfectly balanced on its point that could fall in either direction with the slightest disturbance. This precarious balance means that small changes in fundamental particle masses or coupling constants could push our vacuum either toward guaranteed stability or certain doom. We exist in a narrow window where reality remains stable, but not permanently so. The stability of our vacuum depends critically on the exact masses of the Higgs boson and top quark. Measurements show the Higgs mass at about 125 billion electron volts and the top quark mass near 173 billion electron volts. These values place us uncomfortably close to the instability boundary. Think of vacuum stability like standing on a mountain ridge, where one step in either direction leads to completely different destinations. A slightly heavier Higgs boson would make our vacuum absolutely stable forever. A slightly lighter one would make decay inevitable within cosmic timescales. The metastable regime means our vacuum will eventually decay, but not for an incredibly long time. Standard model calculations suggest decay times longer than 10 to the 100th years, far exceeding the current age of the universe by unimaginable factors. We're not in immediate danger. However, high-energy processes might accelerate vacuum decay by providing the energy needed to nucleate decay bubbles. Cosmic ray collisions, black hole formation, or theoretical particle accelerator experiments could potentially trigger premature vacuum collapse if the energy densities become high enough. The most energetic cosmic ray ever detected carried energy equivalent to a baseball traveling at 60 miles per hour, concentrated into a single proton. These ultra-high energy collisions create conditions that haven't existed since the early universe, potentially probing vacuum stability in dangerous ways. Some physicists worry that future particle accelerators might accidentally trigger vacuum decay. Each new energy frontier explores conditions that could destabilize our metastable vacuum. The Large Hadron Collider operates safely below dangerous energy thresholds, but future machines might reach risky territory. The exact location of the stability boundary depends on currently unknown physics beyond the standard model. Supersymmetry, extra dimensions, or other theoretical frameworks could shift the boundary in either direction. Only future experiments will determine which regime we actually inhabit. Measurements of the top quark mass have gradually improved over decades, slowly narrowing the uncertainty range around the critical boundary. Each new measurement brings us closer to knowing whether our vacuum is truly. Calculation requires knowledge of all particles and forces in nature, including those that haven't been discovered yet. Our current understanding remains incomplete. If our vacuum is metastable, it raises profound questions about the anthropic principle. Did we evolve in a universe with precisely the right parameters for both life and long-term stability? Or do countless universes exist with different stability properties, and we naturally find ourselves in one that hasn't decayed yet? The knife's-edge nature of vacuum stability might not be accidental. Some multiverse theories suggest that universes with metastable vacuums produce more baby universes through quantum tunneling processes. These prolific universe-generating vacuums would dominate the multiverse population. Our precarious position on the stability boundary could result from a selection effect, favoring universes that balance long-term survival with active quantum processes. Perfectly stable vacuums might be sterile environments that produce fewer offspring universes, but the apparent fine-tuning of vacuum stability represents just one example of how our universe seems precisely calibrated for existence. The remarkable fact that we exist to observe the universe provides strong evidence that vacuum decay either never occurs or happens so rarely that intelligent life can evolve before reality gets rewritten. This anthropic reasoning argues that we shouldn't be surprised to find ourselves in a universe with stable vacuum conditions, since only such universes can produce observers like us. Any universe where vacuum decay occurred quickly would erase itself before complex structures could develop. The anthropic principle comes in weak and strong versions. The weak anthropic principle simply notes that we observe a universe compatible with our existence because incompatible universes contain no observers. The strong version suggests that the universe's properties are specifically tuned to enable observation. Consider the range of possible Higgs and top quark masses that allow atoms, chemistry, and life to exist. This range overlaps almost perfectly with the parameters needed for vacuum stability. If either the life-permitting range or stability range were slightly different, the overlap might disappear completely. Think of this like finding that the only habitable planet in a solar system also happens to have a stable orbit. You might wonder whether this is pure coincidence or whether some selection effect explains why inhabited planets tend to have stable orbits. Similar logic applies to vacuum stability. The anthropic principle predicts that measurements of fundamental constants should place us near boundaries between different regimes. We shouldn't find ourselves in the center of stable parameter ranges, where small changes don't matter. Edge positions are more probable in anthropically selected universes. Our position near the vacuum stability boundary matches anthropic expectations perfectly. We exist close enough to instability that small parameter changes could be catastrophic, but far enough into the stable region that vacuum decay takes longer than cosmic evolution time. If the multiverse contains universes with all possible values of fundamental constants, then most universes would be sterile environments where either atoms can't form or vacuum decay happens quickly. Only a tiny fraction would support both complex chemistry and long-term stability. Observers like us would necessarily find themselves in the rare universes that permit both complexity and stability. The apparent fine-tuning of our universe's parameters results from this selection effect rather than from any underlying design or necessity. String theory landscape models support anthropic explanations by predicting enormous numbers of possible vacuum states with different physical constants. Most of these vacuums would be uninhabitable, but the sheer number of possibilities ensures that some support observers. Eternal inflation creates physical realizations of different vacuum states through bubble nucleation processes. Each bubble universe explores different combinations of fundamental constants. Observers evolve only in bubbles with suitable parameters. The anthropic principle also explains other apparent fine-tuning puzzles in cosmology. Dark energy's density, the electron-to-proton mass ratio, and the strength of nuclear forces all seem precisely adjusted to allow structure formation and complex chemistry. Critics argue that anthropic reasoning is unscientific because it doesn't make testable predictions. If anthropic explanations can account for any observed values of fundamental constants, then they don't constrain theories or guide future research. The principle might be philosophically interesting, but scientifically useless. Defenders respond that anthropic reasoning does make predictions when combined with multiverse theories. These predictions concern probability distributions for observed constants rather than specific values. Future precision measurements could test whether constants cluster near anthropic boundaries as expected. The anthropic principle raises deep questions about the relationship between observers and physical reality. Does our existence influence the universe's properties through some quantum mechanical selection effect? Or do we simply find ourselves in one of many universes that happens to permit observation? These questions become even more complex when considering how observation itself might affect the quantum vacuum. In the multiverse landscape predicted by eternal inflation and string theory, parallel universes could exist with vacuum energy densities ranging from nearly zero to values that make space itself collapse instantly under its own gravity. This vast range of possibilities suggests that our universe's vacuum energy density represents just one point in an enormous parameter space. Other universes might have vacuum energies trillions of times larger or smaller, creating completely different cosmic environments and evolutionary histories. String theory predicts roughly 10 to the 500th possible vacuum states, each with different values of fundamental constants, including vacuum energy density. This landscape includes universes where vacuum energy drives explosive expansion, others where it causes immediate collapse, and rare cases where it nearly cancels out, like in our cosmos. Think of this like a cosmic library containing books with every possible story. Most books would be unreadable nonsense, but somewhere in the collection would be Shakespeare's complete works. Our universe corresponds to one of the rare readable books in this vast library of realities. Universes with much higher vacuum energy densities would undergo runaway inflation that prevents any structure formation. Space would expand so rapidly that matter could never clump together to form galaxies, stars, or planets. These universes would remain forever empty and featureless. Conversely, universes with negative vacuum energy densities would collapse almost immediately after their Big Bang. The negative energy would create attractive gravitational effects that overpower normal expansion, causing the entire cosmos to crunch back to a singularity within microseconds. Some parallel universes might have oscillating vacuum energies that change over time. These universes could experience cycles of expansion and contraction as their vacuum energy density varies. Life might be possible only during brief periods when the energy reaches suitable intermediate values. Other universes might have vacuum energies that vary across space rather than time. Different regions would expand at different rates, creating a complex patchwork of rapidly expanding voids and slowly expanding islands where matter could potentially accumulate. The anthropic principle constrains which vacuum energy densities permit observers like us. Values more than about 10 times larger than ours would prevent galaxy formation by making expansion too rapid. Values much smaller might allow too much structure formation, creating universes dominated by black holes. Measurements of dark energy in our universe provide clues about the multiverse's structure. Our observed vacuum energy density sits near the minimum value that permits galaxy formation, consistent with anthropic selection from a landscape of possibilities. Future observations of dark energy's evolution could reveal whether we inhabit a typical, anthropically selected universe or an unusual case. If dark energy changes over time in unexpected ways, it might indicate that our universe represents a rare fluctuation rather than a generic anthropic selection. Some theories propose that conscious observers can influence which vacuum state their universe occupies through quantum measurement effects. The act of observation might collapse the cosmic wave function into configurations compatible with the observer's existence. This observer selection effect could operate retroactively through quantum mechanics' non-local correlations. Our current observations might influence the universe's past history, ensuring that it evolved conditions compatible with our eventual existence. Other theories suggest that vacuum energy densities reflect the information content of their respective universes. Universes with complex structures and abundant information might naturally develop lower vacuum energies that permit more structure formation. The multiverse might undergo a form of cosmic natural selection, where universes with certain properties produce more offspring through bubble nucleation processes. Universes with moderate vacuum energies might be more successful at reproducing, leading to their dominance in the multiverse population. These speculative ideas connect vacuum energy to fundamental questions about consciousness, information, and the nature of existence. The value that determines our universe's fate might depend on subtle quantum processes involving observation and measurement. But the relationship between observation and vacuum properties leads to even stranger possibilities about how measurement affects reality. The quantum Zeno effect demonstrates that frequent observations can freeze quantum systems in specific states, suggesting that conscious measurement might influence vacuum fluctuations and alter the fundamental properties of empty space. This bizarre quantum phenomenon occurs when repeated measurements prevent a quantum system from evolving naturally. Like a watched pot that never boils, observed quantum states resist changing to different configurations. The act of measurement itself becomes a force that shapes physical reality. In laboratory experiments, frequently measured quantum particles remain locked in their initial states far longer than unobserved particles. The measurement process continually collapses the particle's wave function back to its starting configuration, preventing natural quantum evolution from occurring. Think of the quantum Zeno effect like repeatedly checking on a sleeping person. Each time you peek into their room, you reset their sleep cycle back to the beginning. If you check frequently enough, they might never progress through normal sleep stages because your observations keep interrupting the natural process. Some theoretical physicists propose that cosmic consciousness or widespread observation might influence quantum vacuum properties through similar mechanisms. If advanced civilizations throughout the universe constantly measure vacuum fluctuations, they could collectively freeze the vacuum in its current metastable state. The measurement problem in quantum mechanics remains unsolved, making it unclear exactly what constitutes an observation. Does measurement require conscious awareness, or do any interactions between quantum systems count as observations? The answer affects whether observation can influence vacuum stability. If consciousness plays a special role in quantum measurement, then the evolution of intelligent life throughout the universe might gradually change vacuum properties. The cumulative effect of billions of conscious observers could alter how quantum fields fluctuate in empty space. Alternative interpretations suggest that any information processing system can perform quantum measurements, not just conscious observers. In this view, the universe fills with natural measurement devices that continuously observe vacuum fluctuations and influence their behavior. Cosmic microwave background radiation provides a form of universal measurement system that has been observing quantum fluctuations for nearly 14 billion years. This ancient light field might serve as a cosmic measurement apparatus that has influenced vacuum evolution throughout cosmic history. Black holes might act as ultimate quantum observers through their event horizons. Information falling into black holes becomes scrambled and encoded in Hawking radiation, creating a form of measurement that could affect vacuum fluctuations throughout spacetime. The holographic principle suggests that all information in a volume of space gets encoded on its boundary surface. This encoding process might constitute a form of measurement that influences quantum vacuum properties within the volume. Some theories propose that the universe's wave function branches into multiple realities with each quantum measurement. In this many worlds interpretation, vacuum decay might occur in some branches while being prevented by observation in others. We naturally find ourselves in branches where observation prevents catastrophic vacuum transitions. Retrocausal interpretations of quantum mechanics allow future observations to influence past quantum events. Advanced civilizations in the far future might observe vacuum properties in ways that retroactively stabilize the vacuum throughout cosmic history, ensuring their own existence. These ideas suggest that the apparent fine-tuning of vacuum stability might result from self-consistency requirements rather than anthropic selection. The universe arranges itself so that intelligent observers eventually evolve and observe vacuum properties in ways that justify their own existence. Laboratory tests of observer effects on vacuum fluctuations remain beyond current technology. However, future experiments might detect subtle correlations between measurement activities and vacuum fluctuation patterns, providing evidence for observation-induced changes in empty space. The possibility that observation affects vacuum properties connects quantum mechanics to consciousness in ways that could revolutionize our understanding of both. Reality might be far more participatory than classical physics suggests, with observers playing active roles in determining the universe's fundamental properties. But whether observation influences vacuum stability or not, the ultimate fate of everything depends on deeper questions about the true nature of nothingness. Whether consciousness, complexity, and existence itself can survive forever depends entirely on whether our universe occupies the deepest possible vacuum state or merely a temporary stopping point on the way to something completely different. This ultimate question encompasses not just the fate of matter and energy, but the persistence of physical laws, the possibility of eternal computation, and the long-term prospects for any form of information processing or consciousness in the cosmos. If our vacuum represents the true ground state of reality, then the future becomes predictable through known physics. Protons will eventually decay, black holes will evaporate through Hawking radiation, and the universe will reach maximum entropy in the heat-death scenario. But the basic laws of physics will remain constant forever. Heat death doesn't necessarily mean the end of all interesting phenomena. Even in a universe at maximum entropy, quantum fluctuations would occasionally create temporary pockets of order. These fluctuations could produce random configurations of matter that briefly recreate complex structures, including living beings with memories of imaginary pasts. In a true vacuum state, these quantum resurrections would occur infinitely, often over infinite time. Every possible arrangement of matter would eventually appear, including exact copies of every person who ever lived. The heat-death universe becomes a cosmic recycling system that recreates all possible experiences. But if our vacuum is false, then everything changes when decay to the true vacuum occurs. The physics inside a true vacuum bubble might bear no resemblance to current natural laws. Matter, energy, space, and time might operate according to completely alien principles. The true vacuum might support forms of complexity that dwarf anything possible in our current physics. Perhaps the true vacuum allows stable, microscopic black holes that serve as powerful computers, or enables exotic forms of matter that process information more efficiently than any conceivable technology. Alternatively, the true vacuum might be a sterile wasteland where no complex structures can exist. The transition could delete all information, consciousness, and possibility for future development. Reality would be fundamentally simpler and emptier than it is today. Some theories propose that vacuum decay creates baby universes rather than transforming existing space. The decay process might spawn new cosmos with different physics, while leaving our universe unchanged. This could be happening continuously throughout the multiverse without affecting us. The anthropic principle suggests that observable universes must have vacuum states compatible with the evolution of observers. This might constrain the properties of any true vacuum we could eventually transition to, ensuring that it permits some form of complexity or information processing. Advanced civilizations might develop technologies to prevent or control vacuum decay. If vacuum transitions can be artificially triggered, they might also be artificially prevented. Future beings could potentially stabilize our current vacuum indefinitely through technological intervention. Quantum mechanical effects might allow information transfer between different vacuum states. Even if our current vacuum decays, the information that defines consciousness and complexity might survive the transition and reconstruct itself in the new physics. The ultimate fate might depend on whether consciousness represents a fundamental feature of reality or merely an emergent property of complex matter arrangements. If consciousness is fundamental, it might persist through any conceivable vacuum transition. Recent developments in quantum information theory suggest that information cannot be destroyed, only redistributed or hidden. This principle might guarantee that whatever makes existence meaningful will find ways to persist regardless of vacuum transitions. The question of vacuum stability connects to the deepest mysteries about existence, consciousness, and the nature of reality itself. Whether anything meaningful can survive forever depends on physics we don't yet understand, operating on scales we can barely imagine. Perhaps the most profound implication is that nothingness itself might be unstable. Even perfect emptiness could spontaneously create something through quantum fluctuations or vacuum phase transitions. The void that seems like the end of everything might actually be the beginning of something entirely new. The exploration of nothingness reveals that empty space is not empty, that vacuum is not vacant, and that nothing might be the most dynamic and creative force in the cosmos. What we call nothing buzzes with invisible activity contains enormous energies and might hold the keys to understanding existence itself. Our journey through the void shows that the deepest questions about reality emerge from studying what appears to be absent. In learning about nothing, we discover everything. The void that seems like the ultimate simplicity reveals complexities that challenge our most sophisticated theories and push the boundaries of human understanding. The next time you look at empty space, remember that you're seeing the most active, energetic, and mysterious phenomenon in the universe. Nothing is everything, and everything emerges from nothing in an endless dance of creation and destruction that defines the very fabric of reality.